Hey everybody, it's Ripley back again. Today we're going to talk about optimization, wabam, which is sort of the Mercedes-Benz of all word problems. They're pretty beefy and they're a huge application in differential calculus. So what I'm going to do is we're going to do three problems in this video that deal with optimization. And from these problems, I'm going to lay out a set of rules, okay? And then you just follow the rules. Optimization problems can be super difficult and they can come at you from a lot of different ways. But if you follow the template that I'm going to set forth for you, you should be okay. You'll at least have some place to start. And that can be a difficult part or a difficult thing when you're dealing with these types of problems. Okay, so the first problem that we're going to deal with is it's a standard issue algebra 2 problem. You've seen it before and you could solve it with quadratics if you recall. But it's going to be a wonderful example for us to be able to sort of launch from when we deal with optimization problems. So a farmer has 100 feet of fencing and wants, that should be an S, wants to fence in a rectangular pen alongside a barn. What are the dimensions of the pen that maximize the area? All right, now, first things first. Excuse me, I apologize for my handwriting. All right, so let's start with number one. All right, these are the rules of optimization. It will help you. You don't have to follow them, but you refuse to do so at your own peril. Number one is draw a picture if possible. Draw a pic if possible. All right, so in this case, that's pretty easy, right? So I got myself, this is my barn, and then here comes my fence. Okay, easy, nothing to it. It's rectangular. All right, number two, and this is the most important. I'm going to put a star by it. It's the most important thing that you do in an optimization problem. Ask yourself, what is being maximized, or minimized. Optimization just means the best, the most, the least. Like if you're talking about, if you want to minimize cost or maximize profit, something like that. All right, minimized. What is being maximized or minimized? And then this follows directly to 3. All right, write an equation. Now notice it's not a function. I'm not saying it's a function. Write an equation that represents that quantity. That quantity is the wrong word, but that thing, right? So you do that one. You do 2 and 3 in combination. All right. So a farmer has 100 feet of fencing, wants to fence in a rectangle. Blah blah blah. What are the dimensions of the pen that maximize area? Okay. Ask yourself what is being maximized in this case, or minimized. Maximize area. Write an equation. So I'm going to label some parts to this thing just because we know that labeling things makes things easier. So I'm going to call this X and I'm going to call this Y. And I know that the area of this rectangular pen is going to be X times Y. So I did 2 and 3 together. That's always where I start. Write an equation that represents that thing. Okay, now there's a problem. This is not a function of not a function of one variable. It's a function of 2 variables. And in calculus, in this calculus, differential calculus, we're dealing with real valued functions of a real variable. All right, so I need area to be either a function of X or Y. So here's where I come in with a Ripleyism. All right, find a shoehorn. You know what a shoehorn is, right? Shoehorn is the thing that helps get your big feet into your leather shoes, especially if your leather shoes are tight. Find a shoehorn to change the equation from 3 into a function of one variable. One variable. Okay. Oh, that may not show up on the, well, you'll see. Anyway, so what's my shoehorn? Well, all I know is I'm trying to do, oh wait, I got 100 feet of fencing. And I know that if this is Y, then this is Y. So I've got X plus 2Y equals 100. Hey, wait a sec. Can I solve for X in this equation, which gives me 100 minus 2Y, and then stuff, stuff this X into this equation, hey, that makes the x go away, and then I have a function of y. So area as a function of y is equal to 100 minus 2y times y. We might want to take a minute here and turn this into negative 2y squared plus 100y, right? Okay, that's cool. Now, once I have a function of one variable, 5 is easy. Use derivatives to find maxes, mins. Now, in my class, well, we'll get into that in just a sec. We'll have a little addendum, okay, to this. If you recall from your Algebra 2 experience, this guy right here is an upside down parabola. So I know that it does something like that. Excuse me, where this would be y and this would be a of y. And we knew how, using that negative v over 2a thing, we knew how to find the vertex, which represents the maximum area of this thing. The cool thing about calculus is we can do it a heck of a lot faster. Watch, I'm just going to use calculus. A prime to y is equal to negative 4y plus 100. Set it equal to 0. It appears in a puff of algebra that I get a critical value at y equals, if I subtract 100 and divide by negative 4, I'm going to end up with 25. Now, here's a really important thing. So important that we're going to stick it on here. Stick it on our list of rules. There's only 2 more rules. All right? Use a Ripley-Doodle diagram to confirm max, to confirm max min. All right, so let me explain what that means. So I've got a prime. Now let's put 25 on here, but let's think a little bit. In terms of the context of the problem, what are the values of y that make sense? Well, the absolute smallest that y can be is 0, and you better have some really skinny cows if y is going to be 0, right? So I'm going to put an open interval at 0 because it really doesn't make sense to have it be a closed interval. And then what's the biggest that y could be? Well, if we think about that, the biggest that y could be, since I've got y here and I've only got 100 feet of fencing, the biggest y can be is 50. And again, if it is 50, really skinny cows, right? Not real good. They don't produce a lot of milk, and they're certainly not delicious. All right, so thinking about sort of the domain of the function, I realize that the domain of a quadratic is all real numbers, but the domain of the function in the context of the problem can be helpful. All right, now plug in. Let's put in 10. If I put in 10, let's see, I get definitely a positive. Everybody agrees. If I put in 30, I end up definitely with a negative. I draw myself a little stick figure, and I have a max, which is great. Smiley face, woohoo! All right, kind of looks like a smile, but anyway, sorry. All right, now, my Ripley-Doodle diagram confirmed that I have a max at 25. Let me warn you, you may have problems where you get critical values that are actually the opposite of what you wanted. So I could have actually gotten a min at this critical value, right? Because it's a critical value. In which case, because of the extreme value theorem, I would want to test the endpoints of my closed interval. Now, in this case, that doesn't make any sense, right? And clearly, we know that this function represents an upside down parabola. Now, last but not least, and then we'll be done with this problem, we're going to say make sure to answer the question or answer the problem. In other words, have you addressed what the problem, answer the that doesn't make any sense, but I don't care. I'm kind of feeling squishy this morning. All right, answer the problem. Yeah, that looks ridiculous. Answer the question. In other words, make sure that you've done all that the problem asks you to do. So, questione. Question. Bam. Okay, so what does it say? What are the dimensions? Oh, uh-oh. Well, let's change colors of pens just so we know where we're at. Well, I definitely know that y is going to equal 25. So the dimensions, we're giving the dimensions now. Y is going to equal 25, but how do I find x? Now here's the coolest part. this little guy right here, this little shoehorn, as we called it, can always be used to come up with the other information that you might need. Like, had it said, what is the value, how wide should the pen be to maximize area? We'd be done, be 25 feet, right? However, it asks for the dimensions, so I need both the x and the y. Well, I know that y is 25, so I can plug that in, and I know that x has to be 50. So those are my dimensions. Had the problem asked for area, then I could have gone about that in two ways. I could have either found the dimensions first and then just multiplied them, right? 25 by 50. Or I could have, remember, I solved for y. This function right here is the function that spits out areas. Excuse me, so I just take my 25, stick it in here, and I get the same thing. All right, cool. So this is your template that will get you where you need to be. Now I'm going to do two more problems with you. Two more problems. I want to find, whoops, I can't do the whole thing in that. Let's get rid of that there. Thingy dingy. I want to find the minimum distance. This is a great problem because it really helps us out with certain types of optimization problems. Find minimum distance between, between y equals the square root of x and the point, let's do 3, 4. All right? Excuse me. All right, so remember, step 1, draw a picture if you can. So 1, 2, 3, 1, 2, 3, 4, and then I'm going to have the square root of x, which cruises down here. Ooh, clearly not drawn correctly, right? All right, so I want to find the minimum distance between this curve and that point right here. This is 3, 4, and this is y equals root x. Okay? Now, excuse me. Let's go through our question. Let's go through our checklist. Draw a picture. Done. Ask ourselves what is to be minimized or maximized. And the answer to that is distance. Now, what I'm about to say is really, really important. Distance comes from Pythagorean's theorem, right? Now, we all have the formula d is equal to square root of y2 minus y1 squared plus x2 minus x1 squared, right? That is the distance formula. But the problem with this form of the distance formula, excuse me, is that when I take the derivative, I end up with this god-awful, nasty chain rule, right? Because when I take, this is the square root of blah. So when I take the derivative of the square root of blah, I end up with 1 over 2 root blah, d blah, and the derivative just blows up and gets out of hand. So what I'm going to propose that we do instead is I'm going to let big D actually equal d squared. This big D. Because then I've got y2 minus y1 squared plus x2 minus x1 squared. In other words, all that I need is an equation that has these points in it that I can use to at least get to distance. But if I square everything, if I don't deal with the formal distance formula and just kind of revert back to the Pythagorean form of the formula, then I can still get the same critical values. Now you may say, wait a second, Ripley, is that really true? Well, let's think about that. If I have, let's say that I have my x values here, and then I've got my distance squared here, and then I've got my little distance here. Okay, so let's remember distance is always positive. So let's say that x is 2. At x equals 2, my distance squared is 9. When x equals 3, my distance squared is 4. When x equals 5, my distance squared is 25. Now my true distance would be 3, right? Square root, since big D is little d squared, my true distance would be 3, 2, and 5. Well, notice that the critical values, if these were critical values, the critical values that produce the smallest distance produce the smallest distance squared as well. It's not as though the critical value changes at all, right? Makes sense, because if I square distance, then the smallest of the distances is going to produce the smallest of the distance squared, and it makes our job a heck of a lot easier. All right, now enough. Hopefully that gets you where you need to be. I'm going to plug in some points and look at what's going on here, if you don't mind. So D is, in other words, I'm going to work through the stuff that we talked about in this list. I'm a little tongue-tied this morning. I don't know, what's not enough caffeine, I guess. All right, right. We already asked what's being maximized. Write an equation that represents that thing. Done. Find a shoehorn. Well, let's stumble back over here and see about our shoehorn. So let's see. I got D equals, I know it's going to be y minus 4 squared plus x minus 3 squared, right? There's nothing to it. But I need a function of x. Hey, wait a sec. Wait a sec. Y equals root x. Hey, there's my shoehorn right there. So D is equal to the square root of x minus 4 squared plus x minus 3 squared. Well, hush my mouth. Look at that. We've got ourselves not just a distance equation, but we've got ourselves a distance equation as a function of x. Once I have a function of one variable, I get to do calculus. And I'm going to start taking derivatives. Now, some people may want to multiply these things out. And I say, why would we do that? Let's not do that. Let's use chain rule. So I've got 2 times root x minus 4 times chain rule. The derivative of the blah is going to be 1 over 2 root x, which is kind of nice because those 2's cancel, right? And this is going to be 3 times x minus 3 times 1, right, by chain rule because the derivative of that. And then I set the whole thing equal to 0 and I solve. So let's work our way through this and see what happens. Let's see, if I distribute that through, I'm going to distribute the square root of x through. So I will get 1 minus 4 over root x plus, let's see, 3x minus 9 equals 0. So this is equal to 1. No. Let's keep this. Let's make it a little prettier. This is going to be 3x minus 4 over root x minus 8. Let's do that. Equals 0. This is going to be 3x to the, 3 halves, right? If I find a common denominator. What I'm doing right now is finding a common denominator. Minus 4 minus 8 root x. This whole thing is over the square root of x, and this thing equals 0. Now, I'm going to cheat a little bit here. I'm going to pull out my graphing calculator, and I'm going to graph this so that I can find my critical values, because I wasn't very thoughtful when I came up with this point, and I turned this thing into a monstrosity, which if I had to, this would be a cubic, which would be ugly and horrible, but I do want you to look at one thing that's kind of cool. I know for sure that I'm going to get a critical value at x equals 0. Now, that's because the denominator is the square root of x, of this derivative. Excuse me. Now, why is that? Why do we have root x, or excuse me, x equals 0 as a critical value? Well, the reason is because we know at 0, root x ends up with a tangent line, right, that is going to be what? It's going to be vertical. So this thing's like, nah, you're not allowed to do that. That's not cool, right? So a neat thing that you may find as you work through these optimization problems is that the mathematics takes care of any weirdness that might show up in the actual problem. All right, so enough said. Let me grab my TI real quick. I forgot to open it up in advance. I didn't think through what that point would be, so bear with me for just a sec. Close. This is actually kind of a fun little, let's clear that out. And we're going to y equals, and we're going to clear that out, and clear that out. And I'm going to find zeros of this equation. So I get 3x to the 1/2. I've got where am I? I've got 3x to the 1/2. Is that what I said? Or wait, let me make sure. Let's boom, or 3x to the 3/2. Ooh, I'm glad I checked that. So 3x to the, I'm going to go 1.5 because it doesn't really matter, right? And then drop down, keep coming. Minus 4 minus 8 root x. So minus 4 minus 8 second square root of x. And then let's graph it. Give her a quick graph. But bam, that appears to be our critical value. So how do I solve for that? Well, hopefully you guys know how to do that, but just in case you haven't done it before, this is a good time to learn it. But wait, before we do that, let's kind of approximate this. It kind of looks like, ooh, I don't like the way isn't that scale kind of janky? This is 1, 2, 3 and change. But let's confirm. Second calc, let's go to zeros, which is 2. I gotta scooch this guy over, and this is always kind of a pain in the butt because it lags because fighting with all my other systems. Excuse me. Come on, get over there. Get over there. Perfect. Left bound, enter. Right bound, enter. And then enter. I don't want to guess. And I've got 3.391. All right. Now, I'm going to go back to my problem, and let's look at this. I mean, even with my terribly drawn scale, look, I've got 1, 2, 3. This is telling me that this is 3.391. That's the value of x. So this point right here on square root of x appears to be about 3 point something, right? So that's kind of cool. All right. So what do I do now? Have I answered the question? Well, remember, I got to make sure that we're going to do d primed. And I know that x, let's see, I know that x has to be between 0 and then whatever, right? It can range all the way to infinity. I got a critical value of 3.391. Now, this one here is a little bit tricky, but not as bad as you might think. If I put a 1 in, then I'm grabbing convenient numbers that'll keep me out of trouble. If I put a 1 in, I get 3, minus 4 is -1, minus 8 is -9. Sweet, that's a negative. Remember, all I care about is sign. If I put it, let's see, if I put in a 4, right? Because why did I put in a 4? Because I've got these square roots. So I've got 4, let's see, the square root of 4 is 2, 2 cubed is 8, so I have 24. This term becomes a 24. Minus 4 is 20. Minus 16 is positive 4. Yay, look at that. I have a minimum. I have minimized distance squared. Yes, so I have this number. Now, did I answer the question? It says find the minimum distance. Well, what I would do in this case, because remember, all of this work that we've done with distances has been around distance squared. So what I would do is I would take distance squared. I know that d of 3.391 is going to be what? The square root of 3.391 minus 4 squared plus 3.391 minus 3 squared. And that's going to give me the minimum distance squared, which implies that d is going to be the square root of this answer. You know what? Just to be complete, you guys will hate me. Oh, well, I guess now I have to. So second quit. Let's get here. Whoa. Let's get here. Whoa, what is going on? All right. Sorry, you guys. Second quit. And oh goodness, now I got to go back here. Square root of 3.3 minus 4. So, oops, I want that. Let's go here. Square root, I'm going to have the second square root of 3.391 minus, whoops, go back. Let's stick in a paren here just to make it easier. Oh, wow. You know what, you guys? Apparently technology is not my friend right now. We'll just put this guy in and go 3.391 minus 4 squared plus 3.391 minus 3 quantity squared, and then you can crank this thing into your calculator. Enough. All right, cool. That right there is a use of an optimization problem to solve a distance problem. Okay? The most important thing that you pull out of this is that you have the ability to use this distance squared thing rather than taking the derivative of the formal distance formula. You could do the exact same thing that we did, but could you imagine how ugly the derivative would be? So what I'm trying to do is I'm trying to give you a way that's a lot simpler to deal with. Okay? All right. One more problem, one more optimization problem, and then we will be done. Excuse me. All right. That optimization is y are all tuna fish cans the same shape. Now you may say, wait a second, Ripley, what? Why are all tuna fish cans the same shape? Well, if you go into a grocery store and you look at tuna fish cans, it doesn't matter if they came from Bumblebee or Chicken of the Sea or Starkist, they're all the same shape for an 8-ounce can of tuna, right? I got this 8-ounce can, and they're approximately, what do they look like? They're cylindrical, right? Which kind of makes sense. And they got the little corrugation on top, and they got the little rim here and the rim here. Why are they all the same shape? Think about that. Well, it's because for an 8-ounce can of tuna fish, what does a manufacturer of tuna fish cans want to do? They want to minimize cost. But what is cost? Cost is a function of surface area. True? So if I have a fixed volume, if I know that my volume is 8 ounces, and I want to minimize surface area, what this really asks is what is the minimum surface area? Right? We are minimizing surface area because if I minimize surface area, then I'm going to minimize the cost of the materials to make the can. Now, we're going to keep this simple. We're just going to have our tuna fish can basically be a hockey puck because I don't want to worry about the corrugation on the top and the rim on the bottom. There's corrugation on the bottom as well, and that helps the cans to fit together and not slide around. If you just had stacked aluminum hockey pucks, then those cans would slide around. You couldn't store them easily. All right, so let's go through our paces. I already drew my equation. What am I trying to minimize? Surface area. All right, so now we're going to make an equation for the surface area of a cylinder. Well, hopefully you remember that the circumference of a circle is 2 pi r. So we've got ourselves a cylinder, so we better put an r there. And then it's going to have an h, isn't it? So the surface area is going to be 2 pi r h, that gives me the surface area of the outside of the can, plus pi r squared is the area of the top, and pi r squared is the area of the bottom, right? So do you agree that surface area is going to equal 2 times pi r squared? That gives me the area of the top and the bottom that you can't see, right? However, I need to add in this lateral surface area, right? The surface area of the stuff that you're looking at when the tuna fish cans are stacked. So this is going to be plus 2 pi RH. Now, I want to know I guess I should have put the dimensions. Now, the dimensions in this case, I'm looking for the radius and the height, right? But here's the problem. I've got surface area, but it's a function of 2 variables. I've got radius and height. I need to make one disappear. Well, can you think about how to do that? Hey, wait a sec. I know that all these tuna fish cans have 8 ounces in them. And I know that the volume, that 8 ounces is a measure of volume, right? Don't I know that the volume of a cylinder is always the area of the base times the height? So isn't it 2 pi? Isn't it pi r squared h? So I know the volume is equal to pi r squared h, and I know that that has to equal 8 ounces. That's easy enough. If I've got that, then how can I use that? Well, why don't we solve for h? Because I got 2r, I got r here, and I got r here, and I've only got 1 h, so it could be pretty easy to get rid of that. Isn't h 8 divided by pi r squared? Now I have surface area. Notice h is going to disappear because my shoehorn solved for h. So I'm going to have surface area as a function of radius is equal to 2 pi r squared plus 2 pi r times 8 over pi r squared. Now you may say, oh good Lord, Ripley, that looks terrible. But if you just skip it, just pause for a beat and clean it up, I'll get 2 pi r squared. Notice the pi's cancel and one of the r's cancel, and I end up with plus 16 over r. Now I have surface area as a function of r. Sweet! I have an equation of one variable. When I have an equation of one variable, what do? Well, when in doubt, take the derivative, right? This is going to give me 4 pi r minus 16 over r squared, right? Because the derivative of 1 over r would be negative 1 over r squared. Excuse me. Set this equal to 0. let's pause another beat to clean this thing up. I'm going to get 4 pi r cubed minus 16 over r squared equals 0. In a quick puff of algebra, you should be able to see that the critical value is at r equals 0. Now, if I send this across, right, if I solve for the value of r that turns the top into 0, I know the bottom is 0 because it's the value for which the derivative doesn't exist, right? If I send it across, divide through by 4, and then divide through by pi, hopefully you see that this becomes the cube root of 4 pieths, right? 16 divided by 4 is 4. Then you divide that through by pi, and this is what you get. Now, what is that? Let's see, 4 divided by pi, that's basically 4 divided by something close to 3. The cube root of that's going to be really close to 1. So when I'm testing values, then I can sort of numerically come up with an approximation for the cube root of 4 pius. That makes life easier. However, let's test it. I've got SA primed here. What's up, SA? And I throw on, let's see, I know I'm going to stick my 0 on, but why is 0 a critical value? Not just because it was a value for which the denominator became 0 or the derivative didn't exist, but also think about it in terms of this. If r is really, really small, then you're going to have a really long tuna fish can, right? It's going to look more like a straw. Could you imagine, again, skinny, skinny tuna creates skinny, skinny cans. Anyway, that was stupid. All right, let's put the cube root of 4 pius here. And remember, we said that was about 1. Now, we're looking for a minimum, true? So let's pick a value really close to 0, say 0.1, 0.00001. Well, hopefully we see if r is 0.00001, this is going to be a value really close to 0. 0 minus 16, that's going to give me a negative. Let's pick the denominator clearly is going to be positive, right? I'm remiss to not mention that. Let's pick a huge value, 9 million. All we got to do is pick a value to the right, right? 9 million, huge number minus 16, still huge. Bottom still positive. I'm not, well, let's try. No, I'm not going to, well, there's my stick figure. Sorry. Clearly a minimum. All right, awesome. Now the question is, have I answered the question? Have I found r and h? No, I found r. I know that r is the cube root of 4 pius. What do I know that h is? Oh, wait, I can go back to my shoehorn. Look at that, it's tailor-made. It's just sitting there waiting for me. And I end up with 8 over pi times r squared, which is the cube root of 4 pius. And that guy is squared. Now, of course, you would want to use your calculator to come up with these answers in terms of what we said. This is about 1 point something, and this guy is going to be about, I don't even know. 1 point something squared is still going to be, yeah, it's going to be 2, right? I don't know. Now, you may be going, wait a second, Ripley. The tuna fish cans that I see in the store have r is greater than h, and in this case, h would be greater than r. But the reason that is because of all that corrugation and all that packaging. I kept this as simple as possible. However, if I want to have hockey puck shaped cans, these are the dimensions that you have to make the surface area of this hockey puck minimum, to make the surface area of this cylinder minimum. And therefore, all of the manufacturers of tuna fish cans have to make them the same size if they want to have an 8-ounce can of tuna. If they want to have a different sized can of tuna, well, then they're going to have to tweak their dimensions. Okay, whew, that was exhausting. I hope that was helpful to you. That's optimization in a nutshell. Enjoy, and we'll see you in the next lesson.